Corrosive Materials from Chapter 8 in our book, we're going to focus on the pH scale. Now, most of us know the pH scale, at least to some degree, just from kind of our overall everyday interactions with the world. But you may not know what it is or how it's calculated or anything like that. And so from that perspective, let's start looking at what the pH is actually telling us. And so the pH scale is a quantitative description. It's numbers oriented. It tells us the relative strengths of acids and bases to each other, and it does so by telling us and relating to us the amount of hydrogen ion that is present in an acid or a base. Now you may be thinking to yourself, well, wait a second. How much hydrogen ion is there really in a base? After all, there's a lot of hydroxide. Well, what we have to think about when it comes to acids and bases is that neutrality is kind of like a balance beam. On one side, you have hydrogen ion, and on the other side, you have hydroxide ion. And so both ions are actually present at all times in any aqueous solution. And if we have neutrality, then what we will see is that this line is going to be even. It's going to be balanced. But as we go to acids, what we will see is that acids will have a high concentration of hydrogen ion and a relatively low concentration of hydroxide. And bases, on the other hand, will have the opposite effect. They will have a relatively low concentration of hydrogen ion and a relatively high concentration of hydroxide. But we need to keep in mind that all will be present at the same time. We will always have hydrogen ion even in high concentrations of hydroxide. We will always have hydroxide even in high concentrations of hydrogen ion. So the pH scale is really measuring how much hydrogen ion is present. And as far as the scale is concerned, it is on a scale of 0 to 14. It's a logarithmic scale. Now, based on that hydrogen ion concentration, values on the pH scale between 0 and 7 are considered acidic in nature, and those between 7 and 14 are considered basic, which can also be referred to as caustic or alkaline. Now, smack dab in the middle, pH 7 is neutrality, and the substance that we equate with neutrality is pure water. Distilled water has a pH of 7. Everything else is going to vary in some kind of way on one side of the scale or the other. Now, that's not to say that pH of 6 and pH of 8, those aren't terribly acidic or basic solutions. We consider them almost near neutrality, and they have very little acidic or basic properties, but they are technically considered acid or base. Now let's take a look at some features of this pH scale. Each pH unit, because it's a logarithmic scale, it will increase the strength of the acid or the base by a factor of 10. And what we mean by that, let's consider a pH of 2. If an acid has a pH of 2, we know that that acid is 10 times more acidic, 10 times stronger an acid than an acid with a pH of 3. And a substance with a pH of 3 is 10 times more acidic than a pH of 4. Now what's interesting about this scale is that because it's logarithmic, the scale is not additive, it's multiplicative. So if I think of my pH of 2, and my pH of 3, and my pH of 4, we've already established that the step between 2 and 3 and the step between 3 and 4 are each 10x. But what's interesting to note is that if I go from 2 to 4, so if I go from pH 2 to pH 4, I don't get a 20-fold increase in pH. I get a 100-fold increase in strength, because it's not 10 plus 10, it's 10 times 10. So pH 2 and pH 4 are 100 times different from each other in terms of their own strength. And the same is true on the basic side of the scale as well. pH 11 is 10 times stronger than pH 10. pH 12 is 10 times stronger than pH 11 in terms of their basicity. Now, some common pHs and substances that are associated with them. Gastric juice kind of tops out the pH scale here. That's your stomach acid. It is at a pH just below, or just above rather, 1.0. Some other common substances that are acidic, you look at things like tomatoes, which come in right around pH 4. Coffee comes in just under pH 5. Cola and vinegar, which both of which are ingested for various reasons. Those come in just below pH of 3, so pretty acidic stuff, Coca-Cola. Which is why when you see all those other kinds of YouTube videos out there and things that circulate on social media about, things that you can leave stuff in Coke for a day and it'll come back and it'll be completely gone. That's part of the reason why. It's quite acidic stuff. Now, on the flip side, we've got things like baking soda, which has a mildly basic, just a little bit above pH of 8. Milk of magnesia, magnesium hydroxide, its solutions, its suspension, it comes in just a little bit above pH 10. Household ammonia, a little bit smaller than pH 12. Bleach, just a little bit greater than pH 12. So let's review pH a little bit by looking at some practice problems. First practice problem. I've got 3 acids. Substance 1, substance 2, and substance 3. The 3 acids were given those 3 pHs there. Which substance is the most acidic, and which is the most basic? Take a couple of seconds and figure it out. Okay, so let's take a look at this. Now, the pH scale says that the closer we get to 0, the more acidic it is. So substance 1 is the most acidic. The pH of 3.28 is the most acidic pH of the 3. And the one that's the most basic is 3, with its pH of 9.32, which at that pH, I don't know how we could call that substance an acid anymore. Second question. A substance, an acid, has a pH of 3. A second acid has a pH of 6. How many times stronger is acid 1 versus acid 2? Again, let's take another couple of seconds and think this out. Okay, if you need more time, go ahead and hit pause right now. But for the rest of us, let's go through the answer. So let's kind of build a number line here. I've got pH 3, pH 4, pH 5, and pH 6. Now I know between each of these is a tenfold increase in pH. So 10, 3 is 10 times stronger than 4, 4 is 10 times stronger than 5, 5 is 10 times stronger than 6. So the answer here, again, is 10 times 10 times 10. So what we're talking about is 1,000 times the differences between pH 3 and pH 6. So that's the pH scale. Again, really useful in terms of giving us some information about acidity and basicity of a particular substance. What we really need to know out of it is how to use it, how to identify substances as acidic or basic based upon their pH, and then being able to measure relative acidity and basicity based upon pH values. So if you have any questions, please feel free to reach out to me. Otherwise, have a good afternoon.